Michel started his academic career in Orsay, did there is a PhD, then he moved to a postdoc in UCSB with John Clark, then he went back and worked for 15 years in Saclay with his own group working on superconductors, superconducting circuits, and then in 2002 he moved to Yale and is there ever since. So I guess the young generation here knows Michel as one of the pioneers of superconducting-based quantum computers, and that's what he's going to talk about today. I'm not sure that you know that the older generation here knows him as a pioneer in mesoscopic physics. And what's connecting these two things is that Michel had kind of a unique understanding and ability to analyze mesoscopics from the point of view of understanding what does it mean that an electrical circuit that we know from real world goes into the quantum mechanical regime, and even in mesoscopic physics that had a huge impact of our understanding of, for example, single electron phenomena. So today is going to talk in the colloquium, of course, on the effort to make quantum computation with qubits based on superconducting circuits. And in addition to the colloquium today, he is going to give two more kind of seminar mini course talks in Sunday and Monday at 9:30. So, and they would be 1 hour talks in both days. So please come. Okay, thank you for coming.
So I'd like to start this talk by thanking Charles for this nice invitation to present a colloquium here in the Weizmann Institute. As he mentioned, this actually endeavor that I'm going to talk about started, I think, in my opinion, thanks to Joe Imrie, started here almost 30 years ago in this room where there were this, the debates of the conference NOPIMS on one of the first major conference on mesoscopic physics, where a lot of the fundamental, the basic physics of the quantum circuits I'm going to discuss in this talk and in these two courses that I will be giving were developed, and so I would like to take this opportunity to thank Joe and more generally the people here at the Weizmann Institute for their role in launching of this important field of physics. Okay, so what I'd like to discuss today is this rather paradoxical phenomenon where you can actually increase the coherence of a quantum system using dissipation. And this is, in my opinion, a new effect in quantum physics. It's been known theoretically for 20 years. I think we understand it theoretically very well, but the challenge now is to realize it experimentally. And this has started this wish to go in the real world, has launched intense work in various labs around the world, and I'm going to tell you what our own contribution at Yale. So as you have seen, the name Schrödinger cat is going to appear several times in this talk, but what I want to talk about really is Schrödinger's vet. We're going to try to prevent the Schrödinger cat from decaying into being either dead or alive. And first of all, I would like to present the team of people who are involved in this work at Yale. So the PIs here involved in this work are listed on the right, but the people who have actually taken the data that I'm going to tell you in this talk are, on one hand, Zaki Ledgas, who was a postdoc from Paris, a student of Mazia Miraimi. So Zaki started as a theoretician and ended as an experimental postdoc, which tells you that these experiments that we are doing are not that complicated. And on the other hand, we have had the fortune to have also the important collaboration of the important contribution of Nissim Ofek, who was a student with Moti Heiblum, and who was took some of the data that I'm going to present. Okay. And maybe last but not least, I wanted to mention that now at Yale we have this industrial partnership with a startup. There are actually startups building quantum computers in the US. So that's a message. That's just to tell you that people really believe that quantum computers will exist soon. So this is the outline of the talk. I would like to present this collective quantum effect, which some people call quantum error correction. Other people call it Barth engineering or autonomous feedback. There are lots of names for this effect, but basically it's the effect that where you correct, you make a qubit live forever. Then I will introduce our own concepts for doing this, and I will introduce what we call CAD codes with this, which is a new method of encoding quantum information that we think leads itself to this collective quantum effect. And then I'll show you our first experimental results. So I'm sure most of you are familiar with the concept of quantum bits. It's an effective a spin 1/2 system. It can be represented as a point on a sphere, which is nicknamed the Bloch sphere. Every wave function, every linear superposition of two states, 0 and 1, correspond to a point on a two-dimensional manifold. And I'm not going to use this whole manifold in my discussion. This is a bit too complicated. I'm going to use a skeleton of this manifold. So I'm going to introduce 6 cardinal points on the Bloch sphere that are enough to represent all the decoherence processes. All the processes that we want to fight can be understood by just considering 6 points on the Bloch sphere. Basically, if you preserve those 6 points, you're fine. And you see that these 6 cardinal points are, correspond to eigenstates of the Z, X, and Y polymatrices. Okay, so now I'm sure that you're also familiar with the fact that there are several processes involved in decoherence. Decoherence is the loss of quantum information. It's a deformation of this octahedron, of these cardinal points, into a smaller volume. So for instance, you can have a process which is called T1 by people working in NMR or ESR. You have a shrinking of this octahedron, but it goes towards the North Pole. It's energy relaxation. But you can have also a process, a common process known as dephasing, where the North and South Pole remain identical, but the figure shrinks around the equator. So you have a loss of phase here. Okay, so
For example, the point at 0, what does it represent?
the point in the center of the sphere, yes. So in this representation, decoherence in general makes the solid shrink. Basically, you can picture information as the amount of volume enclosed by this solid. So when the solid shrinks, it's not good, but it can shrink in many different possible ways. The point at the center represents the state of maximal entropy. So if you had shrunk this octahedron, which for pure states is tangent to the Bloch sphere, then in the state of maximum disorder, the octahedron would have shrunk to the center. But this means that the randomness, the noise is unbiased. It doesn't distinguish between up and down, for instance. Otherwise, you would get here, if you have energy relaxation, then all the states degenerate to the ground state, to the zero state, and the octahedron then coincides with this north pole.
These points are not necessarily related to these points, or are they?
I'm
Does it
sorry?
mean that the point at z-1 goes in some sense to that point?
Yes, it's overall decoherence is the shrinking, but the shrinking can happen in different modes. So what we want to find is the shrinking. In whatever the situation is difficult, because a qubit is sensitive to 3 independent noises. So the noises, if you think in terms of magnetic resonance, so all the random fields around Z, X, and Y will have the effect of shrinking this solid. But depending on which field fluctuation is strongest, the figure can deform in different manners. And fighting decoherence means that you can fight simultaneously all the noises.
Suppose I'm asking, is this rhomboid or whatever octahedron must be there on the north hemisphere, or can it be anywhere else? Why can it be like this? It's just the volume or the position within the sphere.
So what you want to achieve is you want to preserve this octahedron, and you want to preserve its side. It's the volume that you want to preserve. A deterministic rotation would not really be too bad. That would be a sort of change of encoding, but a change which would be known.
What I mean, for example, a pure state with z equals 1 is still within the new octahedron there, right?
So let me, maybe it's important to mention from the very beginning that we don't want to preserve only one state. So the game is not to preserve only one state. For instance, this ground state or the excited state. We want to preserve all possible combinations at once. So that's why we have to think in terms of this volume rather than a particular point. Okay, so that's the theorem. It's this was actually first discovered by Peter Shaw in 1995, but there were several subsequent work that confirmed this and provided some kind of existence proof that this was true. So it is possible, but of course we don't know the optimal configuration yet. It is possible to preserve quantum information by properly encoding it in a large Hilbert space. So if you have a sufficiently large Hilbert space, and if you have a clever encoding, it will be possible to preserve quantum information for as long as you want. More precisely, for a time which will be logarithmically, which will be logarithmic in the resources that you have. So it basically, you make, if you double your resources, you can make the decoherence time exponentially longer. Okay, so let me give you a sort of geometric interpretation of what this effect means. This effect means that you can somehow find a clever encoding which will have the following property. So you have this octahedron which represents all the superpositions of your basic states, and if the system makes an error, if there is a noise, what will happen will be just either a rotation or a translation of this volume without any shrinking. So this is what the theorem says. And so if somehow you have installed in Hilbert space a restoring force with dissipation, so basically if you have a peg and a spring and some damping that prevents this figure to move too far away, it will, despite the noise in the system, it will remain in place. But of course you need to achieve this situation where the elementary errors only do a displacement or rotation without a shrinking of the volume. So that's the essence of quantum error correction. And of course, many people are trying to really understand this basic question: what are the best systems that do this? And there are various proposals. And here at the Weizmann, people are working, for instance, on topological excitations in semiconductors, which could be a solution in achieving this system. But there are several ways of answering this question. So the pursuit at Yale is to use superconducting circuits. And I'm just going in one slide to give an introduction to this field. I'm going to go very fast. And if you want to understand more about quantum superconducting circuits, please attend these lectures that I will give on Sunday and Monday. But I don't think the talk that I'm giving here requires to know much about this field. So in essence, you have artificial atoms that are circuits, such as the one I have drawn here. They consist of inductive and capacitive elements, and there is one nonlinear element, which is a Josephson tunnel junction. And that is the essential element that gives all the fun in the system. And you can shine a microwave light on this circuit, and the light can do two things. You can, for instance, this green pulse can change the system from one level to another. These circuits has quantized energy level, and some of the pulses will be used to change the state of this artificial atom. And some other pulses, such as the orange one, will reveal what state the system is in. It's chosen at the correct frequency, so that when this pulse goes through the circuit, it will simply be shifted in phase. The circuit won't absorb any of the energy of this pulse. It will be shifted simply in phase. And by using a chain of amplification, which uses a quantum limited amplifier, which is itself based on Josephson junction, you can reveal this change of state. You can measure a shift in phase, and for instance, you can achieve a situation where going from the ground to the excited state of this circuit will shift the phase of the transmitted pulse by 90 degrees, and that can be resolved easily, even if the pulse, the incoming pulse, contains only a few photons. And so this is basically a trace of what comes out of the amplifying chain, basically where we have a signal which is proportional to phase, and we can observe jumps in the state of the circuit. So what is spectacular here is that you can monitor in real time a single circuit, a single macroscopic circuit, and witness the jumps from one quantum state to the next. More precisely, what we can achieve is that we can monitor 2,000 bits of information collected on this quantum system during its coherence lifetime, during its lifetime. And what the noise that you see in this trace is not noise, is mostly not the noise from the electronic chain. It's the noise coming from the quantum fluctuation of the probe signal. The probe signal has currents and voltages which are quantum mechanical variables, and they fluctuate. And when they pass through these quantum limited amplifiers, what you see on the scope at room temperature is really amplified quantum fluctuations. Or another way to say it is that in a quantum optics experiment, when you have a photomultipliers, you have short noise in your detector, and this short noise results from an elementary quantum fluctuation of the optical field. Well, here it's exactly the same situation.
What are the reason of those jumps from ground state to the excited state?
Thank you. That's a good question. So the black and gray trace are two different traces taken at different times. Indeed, the system, if it was at 0 temperature, it would only be in the ground state. It would remain in the ground state. But because the system is not truly at 0 temperature, there's a probability that it can jump up to the excited state spontaneously. What I can say is that when you can monitor a quantum system with such a speed and in monitoring, you don't really care too much about finite temperature, because you are knowing at each moment what the state is, and if you don't like this state, you can manipulate the system and bring it back in the state that you want. That's the reason why this number is so important. You can actually remove entropy from the system by just observing it and reacting on it fast during the next error process. This number is essential to be in the realm where you can do a quantum feedback. Okay, so now in superconducting circuits, there are two different pursuits towards the observation of a qubit with an infinite lifetime. One line of work which is pursued at Google, Santa Barbara, IBM, Yorktown Heights, and TU Delft and other labs, is to basically follow the existence proofs that have been given by Peter Shor and the people who have worked on the early codes. And they are based on a quantum register. We are choosing a completely different route in which we're not going to encode information in a register of quantum bits, but we are going to use actually a simple harmonic oscillator, a superconducting cavity, and use Josephson junction, use artificial atoms to just service this harmonic oscillator, just to provide just the right amount of nonlinearity to manipulate the state of an harmonic oscillator. And this is the basis of CAD codes, which have been proposed by Maziar Miraimi and colleagues in our labs a few years ago. And there were actually similar ideas much earlier developed by Gottesman, Kitaev, and Preskill. So before launching my explanations of why CAD codes are advantageous, I would like to do justice to this other route and present a little bit what it is about. So the best way, I think, to understand this is to look at what is called the 7-qubit code, or also called the STEANE code. So in this code, you're using 7 qubits, so 7 effective spin 1/2, and they are each represented by this little hexagon here. And I have arranged these little hexagons in 3 platelets of 4 qubits, and the 0 logical and the 1 logical, the manifold that is going to be protected, consists of entangled states of this 7-qubit quantum register. Now, this encoding is very clever, and you cannot really perceive all the cleverness when you look at the wave function, but let me give you a few hints. So if you look at these various members of the wave function, and if you look at each of these squares here, and if you count the number of qubits that are 1 or zeros around the platelet, you will see that the number is always even. So there is an internal symmetry in both the 0 logical and the 1 logical that is actually give robustness to this encoding. This encoding actually is robust to first order errors. So what does it mean? It means that you will monitor these 7 qubits and simultaneously acquire 6 error syndromes. You need to measure 4 ways parities. You need to combine 4 Z or 4 X operators to measure 6 type of parities. And in real time, you have to decode these parities and apply a correction to your qubit. So you see, if you can monitor the qubit sufficiently rapidly and do these parity checks, which are very analogous to the parity checks on the codes that you send over the internet, you should be able to correct errors to first order, and therefore prolong the lifetime of the information encoded in the register. But you see that it's quite a lot of, it's very involved, even for this elementary code. And so there is a necessity to find a better solution, something that will be more efficient. So I'm now presenting what the idea behind CAD code. So we're going to use a cavity, a superconducting cavity, which is nothing else than an harmonic oscillator. And what I am representing here is the phase space of this harmonic oscillator corresponding to a cavity. And what I am representing with these portraits in phase space is called the WIGNER distribution, which is, you can think of it as the quantum analog of the probability of finding the system at one point in phase space. The only difference between this WIGNER distribution and the classical probability distribution is that the WIGNER distribution can go negative. So the blue here represents in a way a sort of a negative probability. And I'll explain later what these negative values correspond to. But for the moment, you see it's quite easy to understand what this representation means. So if you have the cavity in the vacuum state, you have a disk centered at the origin. It's colored in red, so everything is positive. But if you have 1 photon in the cavity, you have a slightly larger disk, and you have an oscillation from blue to red. So you have 1 node in this probability, quasi-probability density, and then 2 photons, there are 2 nodes, and so on. Yeah.
What is Q and I descript? Q and I.
Yeah. Yes, thank you. So yes, so I could have plotted, said X and P here. In a case of a circuit, X would correspond to the current and P would correspond to the charge. So actually, I and Q can be understood as actually electrical variables here. But you can think of this also in electrical engineering language. So there is what microwave engineers call the in-phase and quadrature component. So if you think about going in the rotating frame of the harmonic oscillator and measuring an in-phase and quadrature component, these are analogous to X and P. Okay, so there are other ways to excite the cavity rather than using photons one at a time. you can do other types of excitation. For instance, you can displace the vacuum, and that creates a so-called coherent state, semi-classical state. Or you can take this vacuum and squeeze it, conserving, of course, the area here. So this is called the squeeze vacuum. But there are yet a completely different way to excite the cavity, which is to produce the so-called CAT state. So a CAT state is a coherent superposition of two coherent states with opposite phases. So basically, what does it mean? Well, if we would take the analog of a cavity, and that would be a mechanical analog, would be a pendulum. So one coherent state is the pendulum oscillating with a certain phase. This other blob corresponds to the pendulum oscillating with the phase shifted by 180 degrees. And the CAT state corresponds to the pendulum basically oscillating with the two phases at the same time. Of course, if you try this with a real swing, it's extremely hard to do. But with a microwave cavity, as you will see, it is possible. And because basically this would correspond to a true Schrödinger CAT state in the limit where the two blobs would be macroscopically apart, then this is called sometimes a kitten state or a CAT state. So that's why these two cats come in. Okay, so we're not are going to use one cat, we are going to use two cats. Remember, we want to encode a manifold. We want to encode superpositions of states. So we need two basis states. We need a zero logical and a one logical. So the zero logical will be this horizontal cat, and the one logical will be this vertical cat. Basically, everything has been rotated in phase space by 90 degrees. Now, if you observe things closely, you will see that at the center of the fringe here that you see in phase space, the center fringe is red. And the red center fringe means that you have a plus here. You have a plus superposition. And you see that the superposition is even in the two states. And it means that the number of photons, we don't know what it is in all these states. The number of photons is uncertain, but its parity is always even. And that's a very interesting property. So when an error takes place in this cavity, and the merit of the cavity is that there is only one type of error which can take place. It's the loss of a photon. It's the decay of radiation. Then the number of photons will go from even to odd. And so you see that the center fringe here changes from red to blue. There is also another phenomenon that takes place. The cat is shrinking. You see the separation between the two blobs will be smaller. And that corresponds to the fact that the system is losing progressively energy. So you have to repair two things. So we are in a situation where we have not essentially lost any information. We still have any superposition of state between these two states will be preserved. It's just that we have to make sure that before we wait too long, we repair this shrinking of the cat and this flip of parity. Despite the fact that the parity has flipped, the superposition will be preserved. There is also another little effect here, which I have to mention, is that when this zero decays to this state, here there's not any overall phase shift, but when this one decays, there is an overall pi/2 phase shift, which can scramble, well, which will give you a deterministic phase shift in any superposition you had between these two states. So we have to correct this. So this is in a way the encoding we will have. So the 6 cardinal points of the Bloch sphere will correspond to various types of cats. So we have these 2 blob cats at the poles, and on the equator we have these so-called 4-legged cats, which correspond to more complex figure in phase space. And these various states have been realized previously in these experiments, but here what I want to describe is the way we are going to correct the errors that take place on these manifolds. And I will describe our effort in dealing both with the shrinking of the cat, so we can actually repump the cat so that it doesn't shrink. And we can also monitor this photon number parity jumping and repair the states. The type of, in practice, the type of system that we use is the following. So we encode quantum information in a superconducting cavity, and in fact it is this cavity that you see on the left here. It's an aluminum block that has been machined, and it has a cavity oscillating at a few gigahertz. And on the right, what you see is this bigger cavity with a hole in the center, and that is an information dump. So when you want to correct a system, you actually are removing its entropy, but this entropy, you have to put it somewhere. You have to put it in some environment, and in our case, the environment is this auxiliary cavity that is dissipative, that radiates away microwave excitation. And connecting the two is a superconducting quantum bits, which is based on a single Josephson junction that's represented here. An element that is very important in this experiment is that directly connected with the dump here, we have a quantum limited amplifier that monitors in real time what happens in the system. And this amplifier is itself based on a ring of Josephson junction. Okay, so the system is basically a system with 3 degrees of freedom, 2 harmonic oscillators, which is the storage cavity. The other oscillator, which is linear, is this radiative dump, which is a cavity with a hole that radiates information away. And connecting the two is this 3rd degree of freedom, which we call the QUBIT, which is the anharmonic oscillator of the artificial atom. So the Hamiltonian of the system is these 3 bosonic modes, and there are nonlinear coupling terms that couple them. And the one that we exploit, we're going to exploit in this experiment is this nonlinear coupling terms between the storage and the dump that is mediated by the QUBIT. So how do we repair this coherence shrinking? Well, there is a phenomenon that is underappreciated, and it is the following. You need to understand this phenomenon before understanding the explanation, how actually dissipation helps to fight decoherence. So let's take a simple harmonic oscillator evolving in a frictional medium. So this frictional medium is this gray stuff. So when I excite the pendulum, so this pendulum is a driven, damped pendulum, I will reach an equilibrium, a steady state. Classically, in phase space, the steady state is a point, but quantum mechanically, the steady state is a disk. And what is absolutely underappreciated is the following property. The steady state, which is that of a driven dissipative system, so you have a system which is in contact with the reservoir here, well, this steady state of the system is a pure state. I think you have to think about this for a minute because it's absolutely non-trivial. The statement is actually true in the underdamped regime. But in the underdamped regime, the state that is a steady state of a driven dissipative system is a pure state. Basically, it's a displaced ground state of the system. And if you want to compute this pure state, it's very easy. You have a drive, which is this epsilon here. You have the dissipation, which is kappa. So that's the rate at which kappa is the rate at which the photons are leaving. And the coherent state, basically the complex number that describes the center of this blob, is given by the ratio of the drive to the dissipation. But the state is pure. That's the whole point. It's not what we want because we don't want to create a pure state. We want to create a pure manifold. We want a manifold that is pure, not one state. We want to stabilize a whole manifold. But it's a way to get there. So what do we need to modify? Well, we need to modify the dissipative medium. We want a more clever dissipative medium. So we're going to use a dissipative medium which is blind to the phase of the oscillation. A drive and a damping that will not know whether we oscillate this way or we oscillate with the opposite phase. Basically, a drive which is absolutely insensitive to the replacement of x by minus x. So with such a drive and such a dissipation, we will preserve the interference figure that happens when the two blobs are superposed. And we will form a cat. So a system that's driven and dissipates with a special type of drive and a special type of dissipation, which is not proportional to velocity, but to the square of the velocity, will actually form a cat spontaneously. A cat that can be either even or odd. So we have now, if we oppose this type of drive, which essentially sends two photons at a time in the system instead of a single one, and which dissipates with a force proportional to the square of the velocity, not to the proportional to the velocity, the equation we had before has now two solutions. It's again the ratio of the drive to the dissipation, but there is the square root, and now we have two solutions. So we are actually stabilizing a manifold. Not one state, but two states and their superposition. So does it work? Well, it works, and it can be done in the following way. So the way we implement this drive and dissipation is by using this a fourth order nonlinearity of the Josephson junction. So if we take a pump, which lies on the mirror position to that of the resonance of the dump, the radiative dump in which we want to throw away the entropy, we can have the following process. So the junction is going to be a three-wave mixer that does the following things. It will take two photons of the storage and combine them into one photon, which can exit from the radiative dump. So we can remove two photons, two photons at a time from the storage cavity that will hold our quantum information. And at the same time, if we apply a drive here on the radiative dump, we can stimulate the reverse process and transform one photon into two. So the combination of these two processes really implement this effective two-photon loss operator and this effective two-photon drive. Now, it is actually working in practice. So what I'm plotting here is the result of an experiment where we probe what happens, what is the potential in phase space that we have created. We have created in phase space two attractors, which are these 2 points, and the middle point, the point where normally the system would lie in the ground state, has become a saddle point. And this mapping of phase space is realized by starting the system each time in a different position of phase space and looking where the end position will be when you turn on the drive. Now, a more convincing demonstration that this CAD pumping works is done in the following way. So we start with the system in the ground state, and now I'm going to represent 3 types of panels. So the first panel is the raw data showing a raw measurement of the Wigner distribution of the system. The middle panel is taking this raw data and processing it to reconstruct the state of the system, filtering out the noise. And the third panel is a numerical simulation of the system. So, so this is the start of the experiment. We have not started to pump yet. Then after 2 microseconds of pumping, you see the system is squeezing, the ground state is stretching, and then if you wait a little bit more, you will see the apparition of the interference of a cat. It's not a very strong effect, wait a second, but in this preliminary experiment, we had some indications that some superposition was going on. If you pump for too long, then this interference of the two states disappears, because there is still in the system this residual 1 photon losses, and so that mixes the 2 states of the manifold. But in our field, the progress is rather rapid. So what I'm showing now is the result of this year. So we've now reached the point where we can make the 2-photon dissipation be 100 times more effective than the single photon dissipation. So now 2-photon dissipation is really the dominant process, and now we can measure well-developed CADs that spring out spontaneously out of the vacuum. So this means basically that we have this driven dissipative system. So it's a system which is in contact with the environment, and it's still in a superposition of states. So it's a system that sees directly the dissipation, but the dissipation helps actually maintaining the coherence. But, so this is not sufficient by itself. We need to address the photon number parity jumping. So this type of experiment is actually done in Rob Sholkop's group, with whom we collaborate, and they are based on the measurement of the parity of the number of photons in the cavity, so this P operator here. In fact, the Wigner distribution that we present is nothing else than a measurement of the parity of the cavity, but following a displacement of the state of the cavity. So how do we measure the parity of the photon numbers in a cavity? Well, if we look at the line of the qubit, so what I'm representing here is the position of the 0 to 1 transition of the qubit, and its position, the position of this transition is directly proportional to the number of photons. So this is the line when you have 0 photon, this is the one where you have 1 photon, and so on. So it is possible by cleverly exciting the qubit to reveal the parity of of the photon number. So this is done in the following way. Now I'm representing the Bloch sphere not of the manifold that we want to stabilize, but the manifold of the qubit itself that services the cavity. And with the proper preparation of the system, we make it feel the parity of the cavity by a time which is such that all the even numbers are going to correspond to a Bloch vector pointing one way, and all the odd states of the cavity will correspond to a Bloch vector pointing the other way. And now, with a rotation of 90 degrees, we can read out and actually monitor in real time the parity of the photon number in the cavity. And this monitoring can be done in real time with a fast electronic based on this programmable gate arrays. And we can achieve a latency of 200 nanoseconds, so which means that on a time which is really short compared to the qubit lifetime, we can address this, measure this parity and see if it's changing, and basically correct the qubit for these parity changes. So now let me, so in our system we have this artificial atom, this artificial qubit, which we call the transmon. So we are first encoding quantum information in the transmon as a comparison. So if you want, this is a sort of benchmark. So what I'm going to show is how quantum information decays in the qubit first. And as you can see, as a function of time, the qubit disappears, and basically after a time of order 100 microseconds, the information has completely disappeared. The end fidelity here is 0.26%. It's essentially the same as 0.25%, which corresponds to a total disappearance of quantum information. The reason why there is a quarter here and not of 0 is that this is the fidelity of the decoherence process, of the memory process, not the fidelity to a particular state. Now, if we encode the same information, not in the qubit, but in the cavity itself, but performing no quantum error correction, this is what happens. So the information is going to live longer, and after the same time, the fidelity is higher. There is still some information left. But of course, this is no mystery. It's just that superconducting cavities live longer than qubit based on Josephson junction. The really merit of this experiment is shown here now in this third experiment, where we apply error correction. We monitor in real time the parity, and we correct for parity errors. And now you're going to see oops, sorry. This quantum information stored in the cavity and monitored for parity can live longer than the cavity which is not monitored. So I think that I have used your patience, and my time is up. So I would like to conclude this talk. So what we have basically achieved in these experiments at Yale is attaining what we call the break-even point. So the way you know that you have attained quantum error correction, that you have seen this collective effect that maintains coherence, is by encoding information in a collective degree of freedom of the system, and you've done better than any encoding in a subsystem. So that's the claim for success. And in this experiment, which we think is the most advanced of all the experiments on quantum error correction, we have attained break-even point. So we can do at least as good as the best part of the system. So in this quantum encoding, with this correction, we can do as well as encoding information by using a superposition of 0 and 1 photon in the cavity. So if you look at most experiments on quantum error correction, they will show you that the quantum error correction works, but it's still not as good as the best encoding in the best part of the system. So we are barely at the point where quantum error correction begins to work. If you want a comparison with basically fusion energy obtained from fusion, this is where you put as much energy in the system as you get from the fusion process. So this is the state of the art in the quantum error correction, something that I didn't have time to talk about, but which is important. So these CAD states that represent stored quantum information can actually interact with logical gates. There is a possibility of doing entangling two cavities. And of course, there's a certain number of things we have to do to fully demonstrate quantum error correction experimentally. But I would like to end with the following message. So this question of observing this new quantum phenomenon is, in my opinion, purely a question of experimental skill and ingenuity. There is absolutely no hard physical phenomenon that goes against it. It will, in my opinion, happen in the next few years. Maybe us or maybe someone else will invent new tricks, and this will, I think, be very important for the advance of quantum computing. Thank you for your attention.
I want to ask regarding scaling exactly. So one of the strengths of circuit-based quantum error correction is that it can be concatenated to realize fault-tolerant architectures that enable scaling or decoherence to be manageable. Can you concatenate these methods to scale that?
Yes. So the question refers to this the fact that quantum full-fledged quantum error correction relies on different layers of correction. You have to correct errors locally, but you have to correct errors in your correction mechanism and so forth. And once you are in the regime where basically the lifetime of your encoding information scales logarithmically with the resource of your system, you have achieved what is called fault tolerance, basically computing without doing any error. So yes, so the one looming question in all the realizations of quantum error correction is this possibility of nesting different methods. So what is well, the route that is well adapted to these CAD codes is basically an encoding that is based on a completely non-local representation of information. So what I mean is that in the surface code, that is the strategy that is in competition with the one that we are proposing, you are using nearest neighbor interaction, nearest neighbor gates between qubits. So there is a big overhead at the beginning, But in a way, the system is satisfying in the sense that you use only a local interaction. In the route we pursue, we are not at all counting on these local gates. It's possible to, within the scheme we propose, to use nested quantum error correction using non-local gates, which are more efficient. So this is a bit of a specialized discussion, and I'll be happy to tell you more about it.
So a question about the statement said about the break-even point. So let's say that tomorrow you can fabricate the fabrication when you improve your cavity, let's say, the harmonic oscillator, and then you might get better result without quantum error correction, because it's not obvious that it will improve both. So saying that you maintain the breaking even point is kind of specific to a system, and it's not really that you attain some problem. Tomorrow it actually might be below that.
No. So of course, no. It's important when you develop a method to observe this phenomenon that, of course, the method is not superseded by just technical progress on your qubit. But the method I have presented will benefit. Any progress on the cavities and on the qubit will feed directly into this phenomenon. So,
but that's on that would be true to any algorithm, right? And on the practical point, I don't understand what does it mean that on a system you attain a break-even point, because I don't see any meaning to that. Right?
Oh, so right now it is true that attaining the break-even point is not in itself, doesn't mean that we. It's a very important step on the road to full-fledged quantum error correction. Of course, it's not enough. It's not sufficient, but it is absolutely necessary that every experiment that addresses this quantum error correction phenomenon passes at least through this break-even point. That's what I'm saying. You need to at least achieve this break-even point. So if your correction mechanism introduces more errors than what you're correcting, there's no point in using it. The system starts to converge when you are comfortably above this break-even point.
You showed that the cat state that you pump into has an alpha, which is the ratio between the driving and the dissipation.
Yep.
And then you showed that the driving and dissipation are basically the same process. Maybe look in the reverse.
Yep.
Does that mean that you have a fixed alpha that you cannot play with? And secondly, is there an optimal alpha that you would like to play?
Yes. So yes. So what these results show is that by combining this drive and dissipation, you can get a sort of steady-state cat. So this steady-state cat will be basically your encoded information. The encoding is in the parity of the number of what distinguishes the two states is parity, but. Yes, there is an optimal. So you don't want the cat to be too big, because if it is too big, then you are too sensitive to one photon losses. So you don't. That's common to every implementation. You don't want the energy of your encoded state to be too big, because as you make it bigger and bigger, the relaxation kills you more and more. So you don't want too big cats. You don't want too small cats either, because you want to preserve the orthogonality of the two encoded states need to be sufficiently good. But let's say with an alpha of corresponding to 4 or 5 photons in the cavity, that's already pretty good.
One question.
So one of the advantages here was that the cavity has much better Q than the qubit itself, right? So, but the pumping process involves the qubit. So
yes, so you cannot use the cavity by itself because it's impossible to encode any information in a cavity. The system is too linear. So you cannot create any, in order to create any superposition of state that is not the trivial coherent state, that cannot encode anything, quantum, then you need to introduce some nonlinearity. But the trick here is to use the minimum amount of nonlinearity that actually encodes and decodes the state.
So how much are you sensitive in the pumping process to the fact that the qubit is not good? If you had a very
yes, so of course, so let's see. So you can, so right now the cavities are more or less you know, can be 1,000 times better than the qubit. But the qubits don't need to be used, the fraction of the time that the qubit is used corresponds also to this ratio. So that's the idea.
There are no more questions. Let's thank Michel again.
Thank you.